Now, we already spoke about a concept called the kinetic molecular theory of gases. And what this theory did for us is it helped us gain more intuition about how individual gas molecules interact on a very small microscopic level. Now, we also spoke about a law called Boyle's Law. And what Boyle's Law did for us is it helped us gain more intuition about the macroscopic behavior of gases. In other words, what happens at constant temperature when we take a balloon filled with air and squeeze it? Well, we said that, and Boyle's Law explained this, that when we squeeze the balloon, we decrease volume, increase pressure, and eventually our balloon will pop. Now we're going to look at another law called Charles' Law, which also helps us explain the macroscopic, large-scale behavior of many gas molecules and how they interact with one another and with our system. So for Charles' Law to work, two conditions must hold. We must have constant pressure and we must have constant number of molecules. So our N, number of moles, stays the same. And what Charles' Law does is it relates volume and temperature. Remember, Boyle's Law related volume and pressure. Well, Charles' Law relates temperature and volume when pressure is constant. And what it says is that volume is directly proportional to temperature. And this means if we bring the T over, or if we multiply a constant by T, and we bring T over, what we get is the following. V divided by T is equal to a constant. Remember, in Boyle's Law, we saw that P times V gave us a constant, and that if we increase pressure, our volume must decrease while keeping the constant the same. Well, in this case, we have the same kind of situation, except now we have volume divided by temperature. In other words, now, for this constant to remain a constant and not change, if we increase volume, say by 2, our temperature also must increase by the same amount, by 2. So whenever we increase volume, we increase temperature. Or if we decrease volume, we must decrease the temperature for this guy to remain constant. Now notice this constant remains or depends on two things, on the pressure and on the number of molecules. For example, if we have more molecules, our constant will be higher. And we'll learn more about that when we talk about the ideal gas law. For now, it's sufficient to say that our constant depends on both of these guys. So, the same way we did for Boyle's Law, for Charles' Law, we can rewrite this relation in the following manner. Now suppose I have some system, some gas system, and I have two sets of different conditions for this gas system. Well, I can relate them in the following manner, assuming that these guys are both constant. In other words, note that the constant always stays the same when our pressure, number of moles, stays the same. That means if we have some condition V1 and T1 and a second condition of V2 and T2, and these two conditions are under the same pressure and number of moles, that means our constant will be the same. And so I can say V1 over T1 equals V2 over T2 equals that same constant. So once again, for a gas sample with two different sets of T's and V's for two different conditions, this is our law. This is our Charles' Law. Now, whenever we talk about gases and we talk about these different laws that revolve around gases, our temperature is never in Celsius. It's only in Kelvin. And that means we have to convert Celsius to Kelvin. And this is how you do it. To get the Kelvin temperature, you take the Celsius temperature and you add 273.15 to it. For example, if our Celsius temperature is 10 degrees Celsius, I simply add 273.15 and I get 283.15 Kelvin. That's our temperature in Kelvin. So, let's think of an example where Charles' Law is evident. So suppose it's someone's birthday and it's winter, so it's cold outside, and you need to go and buy somebody a present. So you decide to buy him a balloon. So you go inside the store, you fill up the balloon with some helium. Now suppose once you fill the balloon up, there are no holes in the balloon. So the number of moles or number of molecules inside our balloon remains constant. Also, let's suppose that our pressure inside the store and outside is 1 atm, atmospheric pressure. So let's suppose that our pressure is also constant. Now obviously if it's winter, it's much colder outside than inside. So suppose I fill up my balloon with n number of moles of helium, and suppose now I go outside with that balloon. Well, on the inside the store, we were at one condition. We had some V2 and T2, right? Once we step outside, our temperature drops. So what happens to volume? Well, according to Charles' law, this guy states that if we go outside and my temperature drops, then my volume must drop as well to make sure that our constant stays the same. That means if I go outside with my balloon will shrivel. It will become smaller. And that's because of Charles' law. So once again, we see how macro scale events are explained by Charles' law, just like they were explained by Boyle's law. So we have yet another law that helps us explain how gas molecules behave when we have a lot of them together, not simply individual gas molecules. Now we can of course explain how Charles' law functions on an individual level using the kinetic theory. Now kinetic theory explains Charles' law on a microscopic level. At constant pressure, so we have constant pressure, right? Our pressure doesn't change. So if our temperature increases, what happens to the molecules? The molecules gain more kinetic energy. And if they gain more kinetic energy, they gain more speed. They become quicker. And that means the only way that our pressure stays constant with higher kinetic energy is if the volume expands. So that's exactly what happens. In order to ensure that there's constant pressure, an increase in temperature means there's an increase in kinetic energy, and this increase in kinetic energy means that there are more molecules, or the molecules are pushing against the walls of the container with greater force, and so they must expand the container, increase the volume. So let's look at the graph of volume times our temperature. Now temperature here is in Kelvin. So our origin is at 0, 0. Remember, we can't have negative volume. Our smallest volume is 0. So it can't go below this. Now our temperature in Kelvin is 0. So we start at 0, 0. At 0 volume, we have 0 Kelvin. But remember, 0 Kelvin is unattainable. Everything has volume. And that means our temperature must be somewhere above 0. Also notice that V1 over T1 means that our T1 can't be 0. Otherwise, we'd get an undefined number. A number that has infinity as its answer. Because any number over 0 is infinity. So, let's look at this law. Why is it that we have a linear function, linear line? Well, that's because this is our slope, a constant slope, so this guy is constant. Whenever d increases, t must increase by the same amount. If this is doubled, this is doubled. If this is tripled, this is tripled, and so on. That's why there is a linear relationship between v and t, and this is how our graph for Charles' law will look when we graph volume versus temperature.